So let's take a look at the fundamental theorem of calculus part 2, just a quick review before we do number 42 or ones like it. Here's the statement. It says the derivative with respect to x of this function in here. And notice this is a function of x because you're integrating f of t dt. So t is the variable of integration here. So we have a definite integral, but our limits are from a to x. So if I actually evaluate this with the fundamental theorem of calculus part 1, what would I do? I would take the antiderivative. So I'm calling capital F the antiderivative, right? Capital F prime is little f, so the derivative of big F is little f. So we evaluate the antiderivative what? At the upper limit x, and then minus the lower limit a. So that's what we have when we see that. But then if we take the derivative with respect to x of that, what do we get? Well, the derivative of capital F is what? Little f, right? So we're going to get little f of x. And then what about the derivative here? Is this just little f of a? Well, no, f of a is a constant. A is a constant value. So you want to make sure that you understand in this that a is a constant, right? Like, just a fixed number. So the derivative of any constant is 0. So the derivative of this part is 0. So we just get the derivative of capital F, which is little f of x. And that's why the fundamental theorem of calculus part 2 says the derivative with respect to x of the definite integral from a to x of f of t dt is just f of x. And you're kind of like, well, it's just this, is it the same? Is that, yeah. And it's showing the inverse relationship because here first we integrate and then we differentiate. So we're right back where we started from. So if we integrate little f and then we differentiate, we get back to the original function, inverse operation. So that's really what the fundamental theorem of calculus part 2 is saying. So let's look at a couple real quick, one like 42 a through d, which is pretty much just the form. So the derivative with respect to x integral from 5, right? That's a fixed constant. That's like our a above here, right? To x. And here's cosine of, and notice the variable has to be different than x, right? I originally wrote this with an x. I had to change it. But the cosine of the square root of t squared plus 1 dt. So the variable of integration is t. So our little f of t function is cosine of the square root of the quantity t squared plus 1, right? So I mean, I can just, if I've got it memorized, I know what I'm going to happen. I integrate this function, then differentiate. I'm going to be right back to the original function. So if I integrate and then differentiate, right back to the original. But if you want to think about it again in terms of the fundamental theorem of calculus part 1, what is this stuff in the brackets? Well, I would need to find the antiderivative of this function, cosine of the square root of t squared plus 1. And that is not simply sine of the square root of t squared plus 1. That is not the antiderivative. In fact, we would have a lot of trouble finding the antiderivative of this function. It may not even exist as a finite combination of the functions we know. So it may be very difficult or impossible to find the antiderivative. But let's just call that antiderivative capital F. And so what we have in here by the fundamental theorem of calculus part 1 is f evaluate the upper limit, right, capital F, minus capital F evaluate the lower limit. Now I don't know what this capital F is, but I do know that f of 5 is a constant. F of 5 here is a constant. So when I take the derivative of this stuff in here, it's the derivative with respect to x of this stuff in here. Well, I take the derivative with respect to x of capital F of x, I get f prime of x, right? Derivative of a constant is 0. So I just get this. But what is f prime of x? Well, f, capital F, right, is the antiderivative of little f. So when I take its derivative, I get little f. So I get back to little f. And so what is little f of x? Well, I just replace the t here with an x and I get that. So there's your result. There's the derivative. And so here's the powerful thing. I can define a function this way, right? And I can't even get a formula for this function without the definite integral. In other words, I don't know how to get capital F in order to evaluate here. If I can find capital F, I can get a formula for this function in here. This is a function of x. Okay, but I can't even get a formula for that function, but I do know what the derivative of this function is. And that's important because once I have the derivative of the function, I know what? I know where the function is increasing or decreasing, where it has local max and mins, right? I can also determine where it's concave up and concave down, where it has points of inflection, all those things just from the derivative. And so that's a powerful thing. Okay, so that's pretty easy. Look at ones like 42E and F. There you'll notice it looks the same, except instead of going from a constant to X, we're going from a constant to, well, a function of X, something other than just X. Okay, so how does that change things? Okay, well, here's the one from 1 to x cubed plus 4. The function is tangent u to the 4th. Okay, du. So notice my dummy variable in this case is u instead of t. So as long as it's different from x, that's okay. And so the f of u is tangent of u to the 4th. Be careful, that's tangent of quantity u to the 4th. So you're taking u to the 4th power first, and then taking that output and plugging it into the tangent function. Right. So what is this by the fundamental theorem of calculus part 1? Well, it's going to be the antiderivative of tangent u to the 4th. Well, what is that? Well, I don't know. Okay, good luck finding that. It's not easy to do. It's not something that we can find easily. Okay, but whatever it is, I'm going to call it capital F. I evaluate it at the upper limit, x cubed plus 4. I evaluate the lower limit, right? And I don't need capital F because I'm going to take the derivative with respect to x of that now. So what's the derivative with respect to x of this thing? Well, we'll get to that in a minute. What's the derivative with respect to x of f of 1? F of 1 is a constant. The derivative of that is just 0, right? So all I'm looking at, what is the derivative of this? Well, it's not just f prime evaluated x squared plus 4. Remember, we have a chain rule, right? That the derivative of a composition of functions, right? This is not multiplication. This is not capital F times x cubed plus 4, right? This is take x cubed plus 4 and plug it into that function. So f of g of x, right? How do we differentiate? F is capital F, sometimes called the outer function. G is called the inner. So it's the derivative of the outer, evaluated the inner, times the derivative of the inner, right? This, you should remember, is the chain rule. So in this case, the outer function is capital F. So the derivative of the outer, f prime, all right? Evaluate the inner. So the inner in this case, right, is what I'm calling this g of x, right? This g of x. So x cubed plus 4 times g prime of x. Well, I can also write that as in Leibniz notation, the derivative with respect to x. That's what the d over dx means, of x cubed plus 4. So that's the derivative. Well, what's the derivative of x cubed plus 4? Well, it's pretty easy. Power rule, 3x squared. Derivative of 4 is 0, right? So it's just 3x squared. So what is f capital F prime? Well, again, capital F is the antiderivative of little f, right? So it's going to be little f of x cubed plus 4. What is little f of x cubed plus 4? Well, I replace u with x cubed plus 4. So I've done that here. Tangent u is x cubed plus 4 to the 4th times what? The derivative 3x squared. And then if I want to bring that 3x squared kind of in front and write it this way, this is the way you'll typically see it, okay, written. So it's real important. This is tangent of this stuff here when we write it this way. So in other words, I have to take x, cube it, add 4, get that result, raise that all to the 4th power, and then I plug it into the tangent function. That's what this means. And then, of course, multiply that result by 3x squared. So at any rate, there's the result. And so we have to use the chain rule in that one. But I think this idea of thinking about this definite integral in terms of the fundamental theorem of calculus part 1 first, and then taking the derivative will help in this process. Okay, I hope that will help with these.